Okay, good morning. We can start. So before we start, we can just wrap up what or review what we have done. So basically, last week we started same thing, single degree of freedom, but where we have to include the damping, right? As free vibration, as we have, there are three, right? So we have F inertia plus F damping plus F spring or elastic is equal to 0. So in this we have included damping and for single degree of freedom and with this solution. So in the end, when we have discussed that damping is the inherent property which tend to return the structure or control the velocity. And we, in the discussion of last week, we have, there are in general any system, there are four characteristics. Either we are ignoring damping, but when we are uh, considering damping, so there are three characteristics of damping. It depends on to the characteristics of the system, mass of the system. We have underdamped system, uh, which is being explaining with this red, and which is the practical damping, which we are considering like offshore structure. So the motion will be decaying. We have the other two critically damped or over damped system, which means that will be in the first cycle that will be decayed. Then from these solutions we have, because looking at different characteristics, and we have to see that this is the decay. So again, to solve the decay, we have come up to that. We have logarithmically discussed, right? And the effects are we have seen, right? Depending to that, the damping ratio which we have been discussed, that this is the two constant, the actual damping constant and critical ratio of actual to the critical. So this is either this or rho. This is the damping ratio. And most of the structures, because when we are considering, so depending on to the mass distribution into the structure and the stiffness given, so that structure exhibit the natural damping as we are doing this. So this damping what decay in, so that is being depending on to the damping ratio, which is with respect to what is the damping it is portraying and what is the critical damping, which is function of mass. So as we have seen that if the damping ratio is smaller, 2% like over here, so that the number of cycles will go more and the number of cycles will be decaying, right? Because the lighter system or like this, as I have just this, so after certain 7-8 cycles, it stops. If it will be further lighter, the damping ratio will go 1%, so that will be going to more cycle, right? And as we have seen that the damping ratio is getting more and more, so the number of cycle or decay will be after few cycles, right? So as you can see, and we have been discussed normally most of the building structures or even offshore structures, which are being designed for a damping ratio between 5% to 10%, right? Because we would like to maintain, right, the stability and all depending on to the characteristics of material and geometrical sizing. So most of the engineering design for uh, building structure, bridges, or the offshore structures, we have to do. And then we have discussed this decay. So the relationship as in this case, like we have to keep for each cycle, this is the deformation or amplitude. In each cycle as the amplitude is being reducing, but if we are keeping the period of vibration constant, so this relationship x1 to x2, so this decay, so in this case we have discussed that we can represent by logarithmic decrement or with the logarithmic values, and we have come up to that. Then as we say that when the energy, it will be going and returning to the position, or it is slowing. So when it is undergoing to the vibration, so there will be energy. And this energy, when it will be decay, so this energy is dissipating in other form. So the rate of change of energy, as which we have say the energy is basically the work done. So force into velocity, right? As in that decaying, and that we have, and this is the total work done, and that is the total energy which we have to calculate. And then that the rate of energy, or so energy dissipated in viscous damping, which is this, is equal to that what we have discussed. And after that we have discussed some examples. So first two examples we have discussed. So I think this example, I believe, as I told you, this is straightforward, right? So, there are other examples, as here a free vibration test is carried out on an empty elevated water tank. Free vibration test, as we have discussed, that we are not applying the force, excitation force, right? So free vibration means this is like a tower, and you will be pulling from this rest position. So you are applying a static force, and you bring tower or element at certain position. Right? So this is at time t, is because you pull from here to, for example, any distance x, right? And after that, as you pull, right, this tank at distance x, and now you are releasing the force. So when you are releasing the force, you put it at distance x away. So elastic restoring force will tend to return to original position. But because of the this, it will start to vibrate because of the energy stored, right? When you pull to certain, so there will be energy, right? So when you will be releasing, it will not that it will be, because it is, as we say, underdamped system. If it is overdamped or very massive system, so maybe it will go into the, it will suddenly, all energy will be dissipated, right? Because, but if it is underdamped system, so as we are expecting something like this. Right? It will go depending on to the damping ratio of this system. Right? So at time t is equal to 0 when it was x, so something like if you will draw, right? So initial condition time t is equal to 0, it is started like this, right? Because this is x you have already pulled, right? From rest position. So a free vibration, so this is a free vibration test, right? Because is carried out on an empty elevator. This is the tank which is empty as shown in figure 3. The figure we can see. This is the figure, right? And this is what we have to apply the force through this string. A cable attached to the tank which you have applied a lateral force of 144 kilo as we pull, right? So there will be a pulling of 144 horizontal component, right? This is the cable. So you are applying tension in this cable. So this horizontal 144, right? Because we are interested in horizontal component, right? Because lateral lining. For vertical component, it will be going down, right? So we are and pull the tank to 0.05 meter, right? Which means 50 millimeter, right? It pull x is equal to 50, right? When you are applying tension, so horizontally the tank moves to 50 millimeter, right? Or 0.05 meter. Suddenly the cable is cut and resulting vibration is recorded. So when you cut the cable, so the force release and it undergoes to vibration. At the end of 5 complete cycle, right? So it has undergone to the 5 cycle. The time is 2 seconds and the amplitude is 0.035 meter, right? When it was going, so that was the amplitude. So compute stiffness of the system, damping factor or damping ratio, undamped natural frequency omega of the tank, damping coefficient, and the number of cycle when the amplitude become, because when it started amplitude was 0.035 meter or 35 mm, and it is decaying. So at 0.05 or 5 mm amplitude, so what is the number of cycle onto that? So as we have force 144 kilonewton, or we are using the consistent unit Newton meter. So we can say it is 144,000 Newton. Initial displacement is 0.05 meter, right? We are keeping. So the stiffness, because it is elastic, so it is easy. So stiffness is equal to, as we have discussed, force is equal to stiffness times delta or U, right? So you have horizontally rod and this horizontal, and it is linear. So to move the tank to 50 millimeter or 0.05 meter, so we incurred 144 kilonewton force. and it is elastic. So stiffness, horizontal stiffness, so that is the force per deformation. Right? So we have force, we have deformation. So the stiffness of the system is 2880,000 Newton per meter. Time taken for 5 cycles, 2 seconds. So period of damp, because we are considering, right, the time for all cycles is same, right? Because harmonic motion. So we will be considering the time of each cycle is same. So this is TD. So that after for 5 cycle time is 2 seconds. So TD is equal to 0.4 second. So which is 2 pi upon omega d and 2 pi upon TD, which is 5 pi, right? Divided by 0.4. 2 upon 0.4, which is 5. Am I right? The 0.4, 0, so 5. So 5 pi, TD is 4. So the natural frequency is equal to 5 pi radian. Logarithmic decrement from this, right? So 1 upon n, so A1, so in between two consecutive, right? So the n is 5 cycle. So we are looking between 0.05 to 0.035, right? Because we pull to 0.05 meter and the oscillation started from 0.035. So A1 when you pull was 0.5. After that it says 0.035, right? I think this was. At the end of 5 complete cycles, the time is 2 seconds and the amplitude is 0.035. Right? So this is at the end of 5 cycles. So we started with 0.05. After 5 cycles, the amplitude becomes 0.035. So this is how logarithmically decrease. So that n is 5. So this is the logarithmic decrement, and which is equal to this, and logarithmic decrement is equal to 2 pi rho, right? So from there, right, all these formulae which from here. So this logarithmic decrement 2 pi rho or psi is the damping ratio. So from here, so we have calculated logarithmic decrement. So we can, because it is being decreasing, right? The cycle amplitude is decreasing due to damping ratio, so that we can calculate. If we can practically, we can use this, or either we can use that. So here So by looking this, so the damping ratio of the tank is 1.13%, 0.0113. Natural frequency 2 pi upon T, so which means 15.7, right? T is 0.4, so 2 pi upon T is 15.7 radian per second. We have this root again from those equations because this frequency is being this into that is our, so that is 15.7 square. So this is damping period, right? So omega n square into 1 minus rho square is equal to this, right? So from there, rho we have calculated, 15.7 is over here. This is natural frequency of the damped system. So for undamped system, right, because this damping this frequency is modifying. So omega n is equal to 15.7015. T undamped, so very little, right? Almost the same, right? So omega n square is equal to k upon m. So from there, omega n we have calculated, k we have calculated. So the mass of the empty tank is 11682 kg. Right? So with that, all these fundamentals, like equations which we derive, so we can weight W is equal to mg is 114 kilonewton or 11 ton. Damping critical damping constant, so 2 under root km, so which we have, and the damping of the system, so we know the damping ratio is equal to C upon Cc, so the damping that will be 4145 Newton second per meter. So again, from 1 upon n, how many cycles? From 50 mm to 5, right? Because 0.05 is equal to this. So for that, it will go 5 mm or 0.05 meter. So that it will take after 33 cycles, right? Because this from 50, we started, first cycle was 50, right? Amplitude, and we are between 50 amplitude to 5 or 0.05 to 0.005. So what number of cycle? Which is again 2 pi rho, same logarithmic decrement. So damping ratio already known, right? So the number of cycle we can calculate, which is 33. We cannot say 32.43, so 33 cycle. So with that, it is like we can calculate, right? So you have all the formula, right, which is we derive, and with that we can calculate. Now, for example, sometimes in the same thing, right? So it will come that if you will fill the tank with water, let's say it can be further asked. So the weight of water is, for example, 50,000 kg, right? So then again you will be adding all those things and whatever will be needed. So with the addition, how much, for example, stiffness will be changed, right? By adding this, because weight of empty tank, mass of empty tank plus mass of water, and then you can calculate all those parameters, right? Damping constant. So sometimes it has been given by adding the water. So what will be happen to the motion, right? Because the vibration will not remain the same, right? So there are other examples for a small damping show that logarithmic decrement is expressed in terms of vibrational energy U and energy dissipation. This is like a derivation, right? So we have like uh, it is logarithmic 2 consecutive natural log x1 upon x2, or if you will go natural log is any the base is a, right? So this can be written x2 upon x1 is equal to e to the power minus delta, right? Or which is 1. So this become a series, right? So 1 minus delta plus delta square upon 2 plus delta cube upon 3 and so on, right? So this is the uh, series, right? So the vibrational energy of the system is that is stored in the spring at maximum displacement, which is U1 half K x square, which is energy stored, equal to kinetic energy U2 half K2. So U1 minus U2, so this minus this, so you will be uh, divided because simplified, so that you can write down 1 minus U2 upon U1, and in this form that will be 2 delta minus 4 delta square. So delta U upon U is roughly equal to 2 delta. So with this derivation of energy. Now, other properties of damping that we will be, one is the hysteresis damping, right? Because when the system hysteresis, as you, whenever we are doing starting from zero, like loading, unloading, and so like this is the hysteresis movement, right? In any system, right? If you are uh, loading and unloading phase, right? So deformation is going. So real structure and machine do not exhibit the highly idealized form of viscous damping considered it, right? So viscous damping is basically an idealized, right, for this. So that's why the damping is being suffered by this. So when material is cyclically stressed, energy is dissipated with the material itself due to primarily to internal friction caused by slipping and sliding of particle at internal plane during deformation. Right? So again, as if you can look any material, concrete, steel, right? So if you will take the microscopic way of material, let's assume this is some material, right? And this material, uh, if you can say concrete, wood, whatever, so there will be, it is composed of molecules, right? Or small grains, right? Even microscopic level, there will be a small grain, right? So, like you can take the example of our hand, right? So, we will rubbing, right? You feel, so why it feel hot, right? So, so there will be, so same thing whenever we are spacing the material, Right? So there will be, you are applying a force macroscopically. So each particle, so this force through uppermost particle is being transferring, and there will be friction between the particles, that will be right. So depending on to the how you fabricate. For example, the steel you are applying, right? So it is difficult to compress steel with a small force, right? This wood, right? So you keep on increasing, you will get there will be impression form, right? So there will be redistribution because when you are pressing, so while pressing, right? So this particle, this friction, right? So when particle force or so that will be further moving here and there, right? So here what we were saying, it is not purely viscous in real. So whenever we are doing, so our stress in with the material itself due to primarily to internal friction caused by the slipping and sliding, right? Because some energy will be dissipated. This structure, so that will be some will be slip here, some will be slip there. So the material by itself is also causing some of the dissipation. So such internal damping is generally referred to as the hysteresis damping or structural damping, which is like we say it is like unloading, right? Load, unload, right? As what we are. So this form of damping results in a phase lag between damping force and deformation as illustrated in figure 9, which is so like uh, loading phase, whenever a force is being applied, so this is the deformation, right? Like hysteresis too. You are applying the force onto that, so it is deforming, and you go beyond the elastic limit when you are releasing the force. So deformation, some of the force is released, and it is taking to the negative phase, right? As I have pushed, right? This, but this direction, right? This tank, so it is moving there as I put, right? But when it is returning, it is going unloading here and there, right? It is coming this side as well, right? Right? So this is like it is going this into the returning cycle. So during unloading, it is going there, and then this cycle, this hysteresis are going, and this damping is due to the material itself, right? What it is, or it is structural damping, right? Uh, the, so some damping we are getting from the external effects, right? Like the wind, friction, and all. And this is due to by its structure itself, right? If this top will be of steel or aluminum, different material, same force I put, so that the damping behavior will be different, right? So that is as the this is like the loop when this your movement is going in to and fro, right? So uh, this curve is, as we have seen, is the hysteresis because it is making a loop, right? So the area enclosed within the loop represent the energy loss, right? So this is the within this loop, this area because is the energy loss, right? If it is the not returned. So the area enclosed loss or dissipated energy per loading cycle, right? Because it will undergo to number of hysteresis cycle like this, right? So so we can just understand with the simple elastic or non-elastic behavior. So if uh, in general, right, basic solid mechanics, right, you are taking even tension test, right? So you are pulling delta, and when you remove the force, it comes to original length. So within elastic, so this is the loading cycle. So this is because when either you pull down to delta and you are holding, so this energy is absorbed by the system. Energy is not released, 100% energy, right? Because when you brought here, you leave, it come to original position, right? Same thing, right? Elastically, I push at this force, right? So I leave, after that it stops, right? And it stops at its original position. So which means that when I pull to certain millimeters or some distance, so that energy was absorbed by the system. It was in the system. And that is the energy which you call restoring force or something, right? But force into distance is energy, right? So it returned back to the same distance back, right? You apply a force of 10 Newton, move to 5 mm. So you have done F into D, right? So 10 into 5, 50 Newton millimeter work done. This work done is the energy, right? Is stored in the system. And when you release, so this energy used to return it back to 5 millimeter back. So that is the elastic condition, and this is the energy stored. But now you have pulled further that once you release, so it returned to over here, not here, but it returned to over this position. So whenever you pull over here, right? So you went beyond elastic. So there is, whenever you pull beyond elastic limit, so some energy, because now not 100% energy absorbed by the system. Right? Some energy is absorbed, some energy dissipated. Right? That's why it is not returning. Right? So this much energy is absorbed. This much is absorbed, this much energy is dissipated. So that's why when you will be unloading. So when you are unloading, so again, the you start this position, after unloading it is stop this position, right? Which is this elastic. So this amount of energy, right, will be returned back. Right? So when unloading, it is moving and it is stopped here. Right? It is stopped here. So this elastic energy is recovered. Right? So the final will be energy overall. So energy recovered, so which is the absorbed energy and dissipated energy. So this energy was lost, dissipated, and this energy is the recovered, right? Returned back to the system and unloaded. So that equation, again this hysteresis, so we can say that the movement or is initial amplitude sine omega t, and with respect to time first derivative velocity is, so the derivative of this will be omega x sine cos omega t. So the energy per unit, so the damping force, this is the Fd into dx, so that is the energy damping force which is causing in the hysteresis, right? So for small displacement, so that is Fd into dx distance, or which from here Fd, so that will be the 4 from there. So the damping constant h dot d. Right? So the total where we with this integration of that, so this total energy loss is equal to pi neta k x square, where Ce is equal to, from here, critical damping or hysterical damping coefficient neta k upon omega. So based on experiment conducted on the internal damping, it can be proved that the energy dissipated per cycle is independent of frequency and proportional to the square of the. So energy dissipation, which is pi theta k x square, so that is independent of the frequency. So where neta is a dimensionless structural damping coefficient for given material. So normally through the experimental things, so for different material, neta is given, small k is the equivalent stiffness of the system, x is the displacement, and pi is this 2.3. So delta u upon u, which is from there, so hence logarithmic decrement pi beta in hysteresis displacement, so the logarithmic decrement will be defined by this equation. So hence equivalent viscous damping coefficient is given by, so we have to add neta here with natural. So therefore for a structure considered to exhibit hysteric damping or structural damping characteristic, the coefficient neta can be determined by measuring successive amplitude of oscillation as decreasing, right? By then applying equation 3.38 with backslide. Then the structure can be analyzed as an equivalent viscous. So we can, and because we in our analysis we have included so all sorts of damping we are converting to equivalent viscous damping, which where we can use equation 40 CE is equivalent viscous damping due to the hysteretic. So there is one equation, some example for the hysteretic damping. The main span of a bridge structure is considered as a single degree of freedom for the calculation of its fundamental frequency. From preliminary vibration test, the effective mass of the structure was determined to be, this is weight, so we can calculate divided by W is equal to mg, right? So divided by G, so 400,000 kilonewton, and stiffness is 40,000 kilonewton per meter. The ratio of successive displacement amplitude from a free vibration trace was measured to be 1.25. So calculate the value of structural damping coefficient and the equivalent viscous damping coefficient with equation 40 just now. So as this is so this was x1, this is 2 consecutive x2. So what is the drop? So x1 upon x2 is 1.25. Okay. So logarithmic decrement, so which as because this is for viscous damping, right? So that is x1 upon x2, ln x1 upon x2, right? Which is you put 1.25, so a natural logarithm of 1.25 is 0.2231. Can you check? Correct? So that is equal to pi neta. So from there, neta can be calculated. So that is the hysteretic damping coefficient, and the equivalent viscous damping coefficient is the beta k upon omega n. So omega n is equal to k upon n. Both k and m are given, right? So by putting these values, right? So the equivalent damping is to it viscous damping. So that is hysteretic damping, and this is the viscous damping which we normally use in structural design. So which means that other damping effects we can transfer or we can transform to equivalent viscous damping, right? So as with this derivation, with this formula, so normally you are not putting the all which the other damping type we will be discussing, right? Because there. So we will be in our design equation. So all damping will be, we can convert into equivalent viscous damping, right?
Well, how do we know? How do we know if we are dealing with viscous damping or what's this called?
Because that as
Or it's
yeah. So again, there will be, as we will be saying that there will be structural damping, right? A building or even your offshore structure, right? Since you are here, this is your jacket leg platform, right? So due to that, it is vibrating. So there will be for example, the wind, or so that is the causing, like wind, we will be flew, right? So usually this is the external end, that what we have tried without considering structural own things, right? But there will be, right? It is not 100% that there will be due to the external effects, right? So there will be structure itself, right? So that the structural, so just now, as we have been discussed, this NETA for different steel, wood from experimental. Right? So you can also consider that this is from the structural part and its equivalent damping is this, right? Same thing like other effects, like there will be friction, internal friction, right? So other costs we can also be considered, right? So all structure itself, for example, the joint, the geometry, right? So this is structure, so that is causing the damping, right? Because again, this structure, so all these joint internally, right? So there will be some slippage, right? So that will be also helping, right? You are taking, if you can understand structural damping, rubber, right? That's why we are saying that they are having high damping coefficient, right? Rubber you can take, you can press, right? So you are compressing rubber, right? So which means the tendency is that rubber will undergo to the more depression, more compression. Right? So that will, and this is due to the particle, right, reshaping. But when force is released, rubber will come to original position. Right? So that's why in many uh, machine element, right, you can see, or sometimes at home you would have observed washing machine, right? So it vibrates. To avoid the sound, we put something like rubber or something kind of thing, right? So that is, we are, this rubber joint is offering a structural damping. Right? So that's why your structure itself, right? So the joint, so some kind of damping, or like the rubber kind of things will be there, right? So although it will be small, sometimes like a steel structure, we can ignore the uh, structural part, right? But as a structure overall, with its configuration, so there will be some structure itself, material damping. So that's it, that will be. But whenever we will be considering, you will be doing dynamic analysis, and you are taking, as in the beginning we have discussed, that this 5% is the damping ratio, right? That is the viscous damping, right? We are not doing analysis separately. So this 5% will take the overall effect of how much structural, how much viscous, how much this. Right? So that will be taking account of all. Right?
So in the question, if we are given a question, so how do we know from the parameters? How do we know if we are dealing with
Like previous question,
yes, yes.
that was viscous damping
Yeah,
question.
yes. Different from this, what's the
So if it will be mentioned that okay, you have done, and this data or this data will be given, right, of this question. So the previous question and this question will be combined and it will be marked.
okay? But how do we, when I want to solve it?
Yeah. So if in continuation to that, right, so there will be written that this bridge, apart from this, so there will be previous question which is related to viscous damping. So now, if it will be in continuation with this property, it will be, say, calculate the value of the structural damping coefficient. Right? It will be written. This data you are carrying. Right? So structural damping, then you will be going through that. So from there you can say that is the part of the structural damping and this is the then dry friction damping, right? So that the static damping, that is the slippage of the particle, right? So this, but there is something if you are rubbing, right? So this friction will be causing some charge, right? So if you will go to the earlier physics, Coulomb, right? The Coulomb was the first who discussed the effects of the dry friction. Right? So any solid particle, like when again in that example you are moving, right? So you are applying the force. So this there will be friction. So one there will be slippage and friction. Friction will causing the heat. Right? So again something you are heating. So the movement, right, the viscosity will be changed. Right? Right? You are taking some thick fluid. Right? So when you are putting onto the oven, right? So with the temperature, so the flowability will be different, right? So that internal friction, that effects of internal friction, that will be, right? So like the cold bath, right? Whenever you are making, you can experience, right? Steam, right? You will be hitting cold steam. You have to make more effort, right, to reshape. Right? But I'm not sure in your undergraduate you have done some workshop practices where right molding and all, right? So you put this steam into hot temperature and then you can hit, you can give any shape. Right? So that is the dry friction damping. So when due to friction, right, sometimes due to movement, so there will be internal friction as well. And this will also causing the dissipation of energy. Right? So Coulomb damping results from sliding of two dry rough surfaces, like two molecules or particles. The damping force is equal to the product of the normal reaction between the surface and the coefficient of friction. Same thing, physics, right? So the friction, you have two body vertical force. So you are applying the force, and so what is the coefficient of friction, mu. Right? So this force, if you are moving depending on the weight, we can say N mu. Right? This is the friction force, right? You are applying vertical component, right? So the friction force is a part of the vertical component times coefficient of friction, right? So this is horizontal force in between these two. This friction is mu times this, right? From the physics we have learned. So its direction is opposite to the direction of the velocity, right? Why? Because if it is going this side, friction is in the against direction, right? You are, let's say, if you are driving on very rough surface, right? So you are moving car, you need to put more force to speed up, right? Because the part of the force is being nullified by the friction. So, like in the building or structure vibration, so this friction is beneficial to control the movement of the building, right? Because the this is your offshore structure. So wind is moving in this direction. We have to control. So friction internally about this. So friction which is inducing in the opposite direction. So that which means it is a moving force. Right? So we have to control, right? We have to reduce, we have to bring to stationary. So this friction is nullifying, right? This force, right? So which means whatever effort, whatever tendency which is controlling the movement comes under damping, right? Because so internal friction will also cause, right? As we know, the friction is opposite to the exciting force. Right? So friction force will also take part in the in controlling the motion. So this type of damping is used for their mechanical simplicity. To obtain the equation of motion cannot use a single free body diagram. So friction force is given by the mu n. Mu is depending on to the different, again the coefficient of friction, concrete is different, wood is different, and usually we drive by mass, or this force is weight itself. So this force is mass into acceleration due to gravity, which is due to the mass of the structure itself. So that is what we can illustrate over here, that we are moving this mass. You can take, this is spring. So this to and fro, right, is depending on to the friction onto the surface. Right? So this is the motion left, motion right. Right? So that if it is moving here and moving there. So m this when it is motion. So this plus this minus Fd, so net equilibrium, and motion to the right. So because friction will be in the opposite. Friction in this and motion to the left, so FD will be in the opposite direction, right? Because when it is going in this direction, right, motion right, so the FD, the friction will be in the opposite, right? Because friction force will go. So then it is moving, this mass is moving right, friction will be left. So, so this is taking part to move, so that will be, if it is moving left in this direction, so friction will be in the right direction, right? So that will be positive. So each equation is valid for only the half cycle of motion, right? Because whenever your half cycle, whenever you are going right, it is like that. So when you are going right, left, right, is this. So the first part will be applying to this, second part is applying to that. So with this negative and positive, the first equation solution is minus mu n upon k, and the second equation solution, so that will be, because now we are not going to all derivation, right? You will go. So that is from the undamped part, right? We have already come up to when we have in the undamped free vibration, right? So this is the undamped free vibration, and this is because friction damping, right? We have, so first part, so it will go, so it will become minus with that, and for the second part, it will be positive. And then again further derivation, so that will be the derivations of the two equations. So this means that the system vibrates with frequency which is equal to the natural frequency. The constant of the derivation ABCD are determined from the initial conditions again. Let t is equal to 0, again you will put x is equal to x naught and x velocity v naught. So let x naught, x1, x2 denote the amplitude of motion at successive half cycle. So the constants are given by c is equal to x naught minus d, d is equal to 0, where d is equal to mu n upon k. So the equation will become that. So the solution is valid for half the cycle only. For 0 is less than t, t is for half the cycle pi upon omega. When t is equal to pi upon omega, the mass will be at its extreme left position, and its displacement from the equilibrium position can be calculated by this. The reduction in magnitude of amplitude in time for half cycle is 2d. In the second half cycle, the mass moves from left to right. Right? So that will, so this velocity will come 0, and the equation of the second half cycle. So these become initial condition of the third half cycle, and because it is being decreasing, so the motion stops when xn less than equal to d, since the restoring force exerted by the spring force will then be less than the friction force. So the number of half cycle r that elapse before the motion cease is given by this x naught minus rd should be less than equal to d. So r will be equal to number of half cycle x naught minus d upon 2d. So the total motion is described by this figure. So like for example, this is amplitude 10 maxima minus 10 5 5. So starting from here, so this is omega nt, so this can be, so the here we consider the amplitude, this decreases because when this is the decrement, so this amplitude is decreasing at constant rate, right? If it is not constant, so we are assuming this after each cycle, this, so we can apply the logarithmic decrement. Or in rotational form, so we can, so the vector plot is a half a circle with radius x max minus d and center at 0, d located at the left side of the imaginary axis, right? So this is imaginary and real axis. Similarly, the vector plot located at the right side of imaginary axis is half a circle with radius x minimum plus d and center 0 and minus d. So the equation of motion is non-linear in this case. The natural frequency is not changed. With Coulomb damping, it will, because we have seen that the decrement is constant, the motion is periodic. The system comes to rest after some time, theoretically continuous forever with viscous damping. The amplitude reduces linearly in viscous damping, right? As we have seen from the plot, in each successive cycle, the amplitude is reduced by 4d. So xm is equal to, it is reduced, so xm minus 1 minus, because 4d, so 4, this is d. So the slope of the, in one, so that slope line known as like this 4n upon 2m for full, because so this is the potential energy after the half cycle for each cycle is 4d. So this is equation for the system shown in figure this is this figure. So that is the right side motion and left side motion. So each half cycle, W is equal to 1 kilonewton, K 70 kilonewton per meter, coefficient of friction is 0.15, and the initial conditions are initial displacement is 0.15 with zero initial velocity. So S naught and S dot naught is zero. Determine the vibration displacement amplitude after 4 cycles and number of cycles of motion completed before mass come to rest. So FD, which is then the friction force, right? Here damping is friction. So the friction coefficient 0.15, the weight is given 1 kilonewton. So that is, so as we say, omega n will remain. So we can also calculate the natural frequency. So the stiffness is given. This is the mass is 1 kilonewton. So or 1000 Newton divided by 9.81. So that will be 26.8, right? Because the stiffness is given 70, so we have multiplied by 1000, right? So all units are consistent. The time period 2 pi upon omega n 0.2368. After every cycle amplitude reduction, right, 4 FD upon K, right? From there, so FD is 0.15, K is 70 kilonewton. This is kilonewton, so we are putting kilonewton per meter. So that is 8.4 FD upon K. So that will be 8.57 10 to the power minus 3 meter or 8.57 mm. After 4 cycle displacement amplitude, right? So 150 minus this, right? So the initial amplitude is given 0.15 meter, right? Initial amplitude is given and initial velocity is 0. So after 4 cycle, 150. So this is the decrement. After each cycle, decrement is this. So after 4 cycle, amplitude will become 150. Right? Just multiply because it is linearly, right? Here, as we have seen, due to the friction, it is linearly. So this is the rate of decrement from here to here to, so 8 times 4. Right? So that so 150. So that you can draw. So displacement. So free vibration with Coulomb damping. The motion will cease when amplitude of the nth cycle such as KUN less than FD or 2.118. So 150 minus 8 n into 8.57, so should be less than equal to, so from here you can, n should be greater than 17.25 cycle or 18 cycle because it is So there are one. Which time? So from here, right? You so for each cycle is 2D, right? Or we have FD upon K. FD upon K, is it 2.14? We have calculated FD 0.15 kilonewton. Right. And K is 70,000. 70. So 0.15 upon 70 in meter multiplied by 1000. 2 point? Correct? Okay. So then, because how many, so we don't know how many cycles, so 150 minus n times this should be less than equal to 2. So just simplifying this, so this is inequality. So after 17 cycle, so that will be cease, right? Because the condition, as we have discussed here, it will be cease when it will be so that the motion stops when xn less than equal to d, right? So which is with that, right? We say that it will be less than equal to, so more than 17.25 or more than 17 cycle, 18 cycle, it will stop. Okay. I think example 8, maybe I can discuss. A steel shaft of length 1 meter and diameter 50 mm is fixed at one end and carries a pulley of mass moment of inertia 25 kg meter square at the end. A bend brake exert, I think no figure there. It is rotating, right? A bend brake exert a constant frictional torque of 400 Newton meter around the circumference of the pulley. If the pulley is displaced by 6 degree and release, right, determine I the number of cycle before the pulley come to the rest, and 2 the final setting position of the pulley. So the number of half cycle that elapse the angular motion of the pulley. Pulley is right. Uh, so this is like a shaft. There is a pulley. This is shaft. This is pulley. Pulley will be like this, rotating. Right? So the number of half cycle that elapse before the angular motion of the pulley cease. Right? Because when whatever, because your this pulley is taking, so pulley motion is angular, right? So whenever you are uh, hanging something, so either it will go, or when, because pulley is moving, right? When pulley cease, so the number of half cycle that elapse before angular motion of pulley is ceased. So R is number of half cycle less than initial theta naught minus d upon 2d. D is equal to t day. So initial is 6 degree given here, which is in radian, because in engineering calculation we use radian. So Kt is equal to which is the torsional rotational stiffness, and this is the formula of rotational stiffness, Gj upon L. So this is G, J is given 25 kg meter square is the mass moment of inertia. Length is 1 meter, right? And G of steel. So the G of steel, I think it is not mentioned, but we can take here. $79.3 gigapascal, roughly, right? So G is equal to 79.3 gigapascal. So, or 79.3 into 10 to the power 3 Newton per meter square, right? Because we have to set gigapascal. Am I right? Gigapascal to Newton per meter square. 3 or Okay. 1 per mm square. One gigapascal, 1 into 10 to the power 9. So that will be 1 into 10 to the power 9. So, or 79.3 into 10. 9 Newton per meter square. Correct? Okay. So J is the mass moment of inertia, right, for circular shaft, kg meter square. How much? 55 kg per meter square, and 1 meter length is 1 meter. So Gj upon L. G value, what they consider. They did not declare. I think some data missing. This I will check and I will let you know. Because what G is used. Pardon?
The value of L
L is the shaft length.
is 1.
The steel shaft length 1 meter. Diameter 1 meter and diameter 50 mm is fixed at the and carries a pulley of mass moment of inertia at the end. A bend brake this is mass moment. Actually, J we will calculate, not mass. Wait. J of circular section, right? Diameter is given. Circular section. pi by 2 R4, yeah, pi by 2 R4 because it is solid shaft, right? Pi by 2 R4. Okay. Length is 1 meter, dia is 50 mm or 0.05 meter. Right? So J of the circular shaft, solid, it is solid, I think, pi by 2 R4. So pi by 2 into 0.05 upon 2 to the power 4, right? If it is steel and I'm just taking the uh, so the KT, the rotational stiffness, right? G J upon L of the rod. So G I'm taking 79.3 into 10 to the power 9 multiplied by pi by 2 into 0.025 to the power 4 divided by 1. What is the answer? Because all units are 79.3, 10 to the power 9, right? Gigapascal into Newton per meter square. This is also meter to the power 4. Seventy 9.3 E9, right? And J is equal to pi by 2 into 0.025 to the power 4. So this into this So 487 something. Right? 487. Right? Four 487. 48. 48. 48,000. So they have 40 now. So they consider, because the value of G we have taken from the Ethernet now, right? So some they might consider 80 or something, right? Because with grade of steel. Because we with 79.3 value of G, it is constant. We are almost close to that, right? So because they did not mention the value of G, right? So, so because it may be they consider 82, 83 something, right? So the torque is given, which is in the data. So the stiffness, rotational is, this is rotational stiffness, right? Torque is given, right? Band break X. So torque is the force. So so TD is the torque. So 400. So KT upon TD. So R. R is equal to half motion. I think theta minus theta is equal to uh, D is equal to TD upon KT, right? So KT we have calculate D because D is equal to TD upon KT. So TD is 400, right? And KT is equal to, right? D is equal to 400, KT is equal to 49,000. So what is D? So and then 3 point, you can 49,000, right? Roughly. So that is D. So you can put theta. So this TD upon KT. So that whatever value. So theta naught minus this upon 2D. So theta naught put in radian, right? So TD upon KT, which we got, whatever you are getting, TD upon KT, D 400 upon
It's points. That was
0 point something, right? So just if you can say it will be 0.10472, right? Minus 400 divided by 49,000 something divided by 2 into 449,000 something. So this answer is coming, it is correct. So this answer is coming 5.92, right? It is correct. Yeah. Correct. So now this is the angular displacement. So initial was 0.16. So after 6, so 2, because this is 2D, so 6 times 2D. So that will be this minus this. So that will be the, after 6 cycles, the position will be, right? Because 2D, this is value of D, right? So thus the pulley stop at 0.397 degree from the equilibrium position on the same side of the initial displacement. Okay. So this is the circular movement or circular shaft. Okay. So I think this then free vibration with damping of single degree we have. So I think that we stop over here. So we finish. I think this will be forward, but anything you can. So plenty of examples we have discussed. So next week we will start the the exciting, right? The excited force, right? Which means the equation will not equal to 0, right? So that will, so as we discussed that can we have the online class on this Saturday or Sunday? Saturday is fine. Sunday. Sunday, 8 to 10 p.m.
Online?
Online, it will be online.
Next day, 10 p.m.
Or you, or Sunday can be earlier as well.
No. Yeah.
Because some might be some other country, right? So
No PM is okay.
because I'm connecting this, so this Sunday will be what day? Twenty? 23rd to 2025, 8 p.m. to 10 p.m. online. So you are also, you learn X, right? So you learn X platform. But you are on conventional ULearn, because there are two ULearn X, one for ODS, right? Yeah, you are not combined with ODS, right? So I have to place a two, right? So this will be whatever we discuss until today, right? attempted today. 2-hour test, right? But mostly, I will give you all, not derivation, only the problem.
Problems of 2 hours? How many problems?
3, 4. You will see.
Oh, just 3, 4 questions. Long problems. Long problems.
Yeah, what we have discussed, what many problems we have discussed, but in a more comprehensive way. 2, 3 problems I will combine in one question. It is 2 hours. But you have all your lectures with you, right? And I have also shared book as well with you, right?
So how can we submit it? How do we submit it?
Pardon?
How do we submit
Online,
it?
online, submit online.
And how can we write answer the question?
Yeah, you can write down on copy and scan. You can scan and submit.
Okay, so on the paper.
You people, you are familiar with online, right? Last time, lockdown time, all exams were online. So yes, you will write down on your copy, scan and put before time.
But 2 hours is
So, but don't communicate. Okay? Because I'm just keeping same way as ODL, distance learning. Right? So because I have to take online, so I can put you as well online. Okay? I think more or less all type of problem we have discussed. So you do your good practice, right?